going to discuss algebraic expressions and simplification. So we begin Unit 2 today, which is all about algebra. And algebra is really the system of math that involves unknown pieces. And so this is the introduction of the unit where letters become a really important part of mathematics. Why do we use letters, really? It's probably a good place to start. Remember that we use letters to represent things that we don't know yet. And these letters are referred to as variables. For now, we're just going to mention variable as a symbol in place of an unknown value. And math allows us to use certain processes to find out what that symbol represents or what that unknown really is. There you go. And so we use these variables in places where we don't know something, and our goal is to work backwards to find out what it is. Now, algebra obviously gets really complicated later on, and it can really just start out complicated because now you're mixing in numbers and letters, and the rules seem like they've all completely changed. So it's important for us to talk about what we're doing in the process of seeing these letters. How should we be attacking these problems? What do we look for in order to tell us how to attack these problems? And the first thing that we need to talk about in algebra then is the difference between an expression and an equation. Now, both algebraic expressions and algebraic equations have a combination of numbers and letters in there, but there are certain things that we can look for to tell us that we're dealing with an expression or dealing with an equation. And then once we do that, we can start discussing the process that we use in order to attack certain problem types. And so I'll give you an example of each one first. Let's see. Perhaps I have something like 3x minus 5 as an expression over here. And on the other side, I'm going to put an example of an equation, maybe something like 3x minus 5 equals 16, something like that. And so the first thing that we can notice, the difference between these, is that the equation has an equal sign in it. Anytime that we see some sort of algebraic statement that has an equals in it, then we know we're dealing with equation. Another thing that we should look for, or in the case of expression, notice that we don't have an equation. And so that's a good way to identify that we're dealing with an expression compared to dealing with an equation. So once we've determined whether we're dealing with an expression or an equation, then we need to find out what are we asked to do with these things. Well, most commonly for equations, we're going to be asked to solve for the unknown. In this case, the unknown, I'm using the letter x. And so the directions oftentimes, pretty much every time, for an equation is going to tell us to solve. In other words, we want to know what is this letter, what number does this letter represent in order to make this statement right here true. What number would I have to plug in to make 16 equals 16? And in the next couple of videos, we're going to talk more about equations and the process that we use in order to find out what that x value is, instead of just plugging in random numbers to see if they work. But for now, we're going to discuss a little bit more about expressions. Expressions can have two different sets of directions. Not solving, though, remember that's going to be for equations, but the different expression directions we can have can be to combine like terms. This is also called simplify. And then the other set of directions that we can have for expressions can be to evaluate. So we'll talk about what both of these directions mean and how we take care of them. To combine like terms, or to simplify, means that we look for lots of different values in an expression. Some of them may be similar and some of them maybe not. And our goal is to rewrite it in a simpler form by combining the ones that are alike together and then leaving the ones that are unalike apart. In this case, anything that has an x attached to it is going to be a variable term, and any term that doesn't have x to it we'll refer to as a constant term. in this expression right here, 3x minus 5. That's already simplified as much as we can. There's only two terms in here. There's only one term that has x, and there's only one constant term. But I could have one, maybe let's combine like terms in a different example. And we'll do maybe, let's see, how about 2x plus 5y minus 8x plus 10xy minus 6y minus 7xy. So here we have a much more complicated expression. Oops. Still, it doesn't have an equals in it. Our goal for this problem will be to combine like terms. And when we do that, what we do is we want to identify how many different types of terms we have in here. It looks like in this problem we have 3 different types of terms. Now, how do we determine what's a type of term? We look at the unknown part. We look at the variable. In this part right here we have an x, and it's raised to the first power. The only other terms that we can combine with this x to the first power, this first term right here, is any other term that has an x to the first power as well. And so this y value doesn't work. Here we have a minus 8x, so that is a like term as well. And then we go on to these other terms that have x and y in them, and they are its own animal as well. So for terms to be like, they must have the same variable, and that variable needs to be raised to the same power. So an x to the first power and an x squared are not like terms. An x to the first power and another x to the first power are like terms. When we combine these values, what we're doing is we're using our rules from combining integers that we learned in the last unit, and we're basically just adding or subtracting the numbers out in front. So again, we always identify whether these terms are positive or negative, and then we combine them accordingly. Here I have a positive 2x in the front and a minus 8x in the back. And so when I combine these, a positive 2 and a minus 8, it's going to give me a negative 6. And the x value does not change. So basically, I had positive 2 of them here. I had negative 8 of them here. When I combine those values, I now have negative 6 of those x values. We can continue this problem by combining the y values. I have a positive 5y here that I underlined with 2 lines. And then way over here, I have a minus 6y, and I can combine those as well. A positive 5y minus a 6y is going to be left with a negative 1y left. So you can write this as negative 1y. Sometimes we don't write that number in the front if it's a 1. If there's no value there in the front like this, just negative y, it means negative 1y. And so sometimes we don't put that number in the front if it's a 1, but if it helps you to remind you that it's there, you can certainly put a 1. And then the last thing we need to combine, which I'm going to underline with 3 lines, are these terms that have x, y in them. They have the same variables, both x and y, and both x and y are raised to the first power. So we can combine those as well. I have positive 10 of them here, and then I'm going to combine that with negative 7 of them here, which is going to leave me with positive 3 of them left over. Don't forget to put your variable on the end, x, y. And so now we took an expression that had 6 terms and we wrote it in a more simple form. Now it only has 3 terms. And notice none of these terms can combine because they all have different variables. This first term has an x, this second term has a y, this third term has both x and y in it. And so that's the first way that we can attack expressions. And that's really that process of simplifying by combining like terms. Now there's more that we can do with expressions. Another important thing that we're asked to do with expressions is to evaluate. To evaluate an expression, really means to plug in for the unknown. So we can be given an expression. I'll put one out here. For example, we could be given something like, I don't know, let's do this first one. 5x minus 7. Here's an expression. Doesn't have an equal sign in it. The directions in this one are going to tell us to evaluate. Now we can't go any farther yet until we know what to evaluate. We want to plug in for this unknown x, and in this problem they told us evaluate when x is equal to negative 3. And so what our goal is here is to take our negative 3 for x. We're going to plug it in for the y value, and then we're going to have an expression that has all numbers in it. We can use our order of operations to simplify that, and our answer is just going to be some number. So let's plug in and find out. We get 5 times a negative 3 minus 7. Then we use our order of operation rules in order to simplify. We'll take care of the multiplication first. 5 times a negative 3 is going to give us negative 15. I bring the minus 7 down, and now I can combine these two. Negative 15 minus 7 is going to give us negative 22. So when we're evaluating, our answer should be coming out numerical all the time, particularly if the unknown value right here is a number. So for these problems, that's all you're going to see. You'll just see numerical values in there. We plug them in, we use our order of operations, and we simplify. So we've talked about evaluating algebraic expressions. We've talked about simplifying algebraic expressions by combining like terms. So we have one more thing that we want to talk about, and that is translating algebraic expressions. Translating algebraic expressions is going to be extremely important when we get to word problems. So to translate algebraic expressions really just means to take the words that are given to you and write that in math form. And so it's going to be important first to come up with a list of words that we use in order to determine what math operation we're doing. And so before we do any problems, let's run through just a few of those. So here are some words for addition. Certainly add would be one. The word sum is another one. Total also is a good one for addition. And then lastly, plus. These are all good words that tell us when we're dealing with words to a phrase that these would be an addition going on. Subtraction has a similar set of words, of course, subtract. The word difference also means subtract. And I'm also going to put in here minus. I forgot on the other one for addition. Let's put more than. 8 more than a number means to add. Also less than. 5 less than a number means to subtract. I'm going to put a star here by subtraction because it's a little bit different than the other four operations that we're going to be looking at. Subtraction usually is written backwards. We're going to do an example where we see that. It doesn't matter too much in addition because it is commutative. 3 plus 7 is the same as 7 plus 3. But in subtraction, that order does matter. So we have to be really careful in the way that we write it out. 2 more sets of values that we can look at. Multiply. The important ones for multiply would be product. Also times. 8 times a number means to multiply as well. And then we'll put one in here for divide. And the most important ones for divide is quotient. So with that in mind, let's take a look at some of these algebraic expressions and see if we can turn the words into math symbol. Start with the first one here. It says 5 more than x. So more than means that we want to increase this number by using addition. And so we want to have 5 more than x. We could write this as 5 plus x, or more traditionally, we would write this as x plus 5. If we want to increase something by a value, you normally just put it on the end. This is much more important for subtraction than it is addition. So if you wrote this as 5 plus x, that would be okay. But I'm going to get in the habit of writing that variable first in these cases. Well, let's look at a couple others. 10 times a number x. And so this one I'm going to write it as 10 times, of course, means multiply. I'm just going to put the dot here for right now. So you could write it like this, 10 times x, or more formally 10x, like this. When we're looking at multiplication, we like to put the number out in front. That number has a name. It's called a coefficient. And then, of course, we know that the unknown piece we refer to as the variable. We'll do a couple more. Two subtracted from x. So when we read it left to right, we feel like we want to put 2 and then minus x. But really what that's doing is it's starting out with 2 and taking x away from that value. And really what we want is the opposite of that. If we want to subtract 2 from a value, then it goes on the end. That's why I put that star on subtraction, because it's kind of backwards. Even though when we read it left to right, it looks like 2 minus x, we really want to express this as x minus 2. Imagine x was 100. 2 subtracted from 100 isn't 2 minus 100. It's starting out with 100 and taking away 2. And so that's why in the subtraction we want to make sure that we write that backwards. Okay, we're going to write that the other way around. It's always good to plug in a number if you're not sure and see how it makes sense in terms of writing it, if it matters to write it forward or backwards. The last one we'll look at in here is 9 more than 5 times w. So 9 more than something means that we want to add 9 to it at the end. So I'm going to start just by reading that part, and at the end here I'm going to put plus 9. And then we have this other piece right here, 5 times w. According to our order of operations, the multiplication should be going first before this addition. And it's also closer, right? It's written right next to one another. So 5 times w we know should be expressed as 5w. Now in this particular problem, it doesn't matter if you wrote it as 9 plus 5w, or the way I prefer to write it, 5w plus 9. But if this was a subtraction, if it said something like 9 less than 5 times w, then you'd want to make sure that you write it in this form so that that 9 is left over on the end. And so now we've done a handful of these. You'll have more opportunity to work on these as well. And the last thing we want to talk about is the distributive property. Oftentimes in algebraic expressions and in equations, we're asked to evaluate or look at the distributive property. And what the distributive property really tells us is that if we have a number out in front, I'm just going to use one here. I'll make this bottom one looks good. X minus 1 plus 2 times 3x plus 1. The distributive property is designed for us to use multiplication on the outside of parentheses when we can't simplify what's inside any farther. So notice in here we have an x minus 1. These are not like terms. This one has an x. This one does not have an x. So we can't really simplify what's inside of here any farther. So instead what we do is we take the number that's on the outside, which is supposed to be multiplied by this thing, and we bring it inside and we multiply both terms by that number separately. When we do that, we don't need the parentheses any longer. So what I'm doing here is I'm taking a negative 7. Remember, we always trust the sign to the left of a number. We take this negative 7 and we bring it into both of these terms inside. I get a negative 7x, and then here I have a negative 7 times a negative 1, which is going to become a positive 7. And so what I did is I distributed my negative 7 inside, and now I don't need the parentheses anymore. Similarly, I'm going to do the same thing to this value 2. Notice that it has a plus here, so this is a positive 2 that I'm bringing into both of these terms. When I multiply a positive 2 times 3x, I get 6x. This also brings up an important point. We talked about combining like terms. When can we combine terms? So notice inside here, we can't combine these because this term has an x and this term does not have an x. but these terms are being added and subtracted to one another. That's when we have to be careful about like terms. When we're multiplying, which is what we're doing here in the distributive property, that rule of like terms doesn't matter anymore. It's only when we want to add and subtract terms that we have to group them up. For multiplication, we don't have to worry about that. So this positive 2 can get multiplied by the term with x, and it can get multiplied by the term without x, just as easy. So when we multiply the 2 and 3x, we get 6x. We multiply a positive 2 and a positive 5, we get positive 10. So now we've completed the distributive property, but we're not done yet because we want to simplify this. Notice that we have 4 terms here. 2 of them have x, and 2 of them are just constants. So we can combine the x terms first. I have a negative 7x and a positive 6x, which is going to give me negative 1x, or just negative x. And then when I combine the numerical values, or the constants, I have a positive 7 and a positive 10, which is going to give me a positive 17. And that's as far as I can go in this problem. I can't combine this minus x and the 17 any further. They're separated by addition and subtraction, and they are not like terms. So that's it for algebraic expressions. In the next videos, we'll talk about solving equations by using ratio and proportion, and talking about the rules of algebra to isolate x.